Alright, hello everybody. So today I'm going to be going over the HNMR chart. I'm going to talk a little about what shielded and deshielded mean, when does something have low frequency, when does it have higher frequency, or low chemical shift, high chemical shift. So this is my chart. I want you guys to know everything on the right is my shielded, my low frequency, low chemical shift, and upfield. So those words right here, they always go together. So whenever somebody tells me I have a hydrogen that is shielded, it's the same thing as saying the hydrogen has low frequency or has low chemical shift. And also note that low chemical shift is the exact same thing as upfield. So again, whenever something is shielded, that means usually it does not have an electronegative atom nearby. And this is something really good to know. My electronegative atoms, whenever they're nearby, that usually tells me that I have a higher chemical shift. So if I don't have them, it's low chemical shift. And I wrote some of my electronegative atoms right here. That's some examples right here. So some examples are oxygen, fluorine, nitrogen, chlorine. And usually anything that's on the top right of the periodic table, that's usually high chemical shift. Just also a quick reminder, your noble gases are not electronegative. So what does it mean when I say something is electronegative or something that is on the top right of the periodic table? This usually means that it really lacks electrons, and the electrons will spend more time around the electronegative atom. So let's do just a quick example right here. So if I have a CH4, let's say I have a bunch of electrons. This is just to demonstrate the point of this. Let's say I have a bunch of electrons. They're just going to be equally distributed everywhere, because there's not that big of a difference in electronegativity between hydrogen and carbon. They're both considered to be not very electronegative, so the electron distribution is going to be equal. They're going to be everywhere. But if I have something like water, and we know that water is very very polar, because oxygen is very electronegative. When I'm going to draw just a bunch of electrons, my electrons are going to tend to be more near the oxygen and less near the hydrogen. I'm going to have a bunch of electrons near the oxygens, or my electrons are going to spend more time near the oxygen, because oxygen is very electronegative. So in this case, because my electrons in the CH4 are spending equal time around the carbon and the hydrogens, I'm going to call my hydrogen shielded, because it still has its electrons are still shielding it, they're still around. But whenever I'm talking about water, for example, something like very polar, when I have something that is electronegative, like oxygen inside of it, if you notice, the electrons are spending a lot more time near the hydrogen near the oxygen than the hydrogen, making my hydrogen deshielded, so it's not shielded anymore. So deshielded means my electrons are not near the hydrogen anymore. Shielded means the electrons are still around the hydrogen. And again, just quick quiz. If something is shielded, does that mean it's upfield or upfield? Sorry, does that mean it's high frequency or low frequency? If it's shielded, right here, should you expect high frequency or low frequency? And the answer is low frequency. What about chemical shift? Is it low chemical shift or high chemical shift? If it is shielded, it's also going to be low chemical shift. What about upfield and downfield? That one can be a bit more confusing, so take a second and think about it. Is it going to be upfield or downfield? So shielded is going to be usually upfield, right? So this is what I wrote right here. If you look at it right here, shielded is going to be with low frequency, it's going to be with low chemical shift, and it's with upfield. Alright? So let's do some examples. Let's look at this one first. This hydrogen, we consider that to be shielded because if you look around, there's no electronegative atoms anywhere, right? No electronegative atoms anywhere. That tells me it's shielded, it has low chemical shift, and it's going to be upfield. So in this example, what I did, I introduced an electronegative atom. In this case, it happened to be an oxygen, but I did not put it right next to the hydrogen. It was just somewhere in the molecule. What this tells me, this is going to be less shielded than the first example. If you look at the first example, there was no electronegative atom whatsoever, so it was very, very shielded. It was just the most shielded it can be. But in this case, the second I introduce an electronegative atom, now it's less shielded than the first example. And it's going to have a higher chemical shift than the first example. The next one, I introduced a Y. A Y in this example just means it's an electronegative atom. It can be, some examples can be like fluorine, chlorine, doesn't matter what Y means. Just know that Y is an electronegative atom. So if you look at this example, the hydrogen is closer to the electronegative atom than the previous example, right? So because the hydrogen is closer to the electronegative atom, it's only one carbon away, if you notice. Well, in example number 2, it was 2 carbons away. So because it's closer to the electronegative atom, it's going to be even less shielded than the first one and second one, and it's going to have a higher chemical shift. Right, if you look at the next one, in this example I'll give you like, R can be anything by the way, it can be like CH3, it can be anything. So I give you a hydrogen that is on an oxygen, and again, oxygen is very electronegative, so this is going to be even less shielded. My hydrogen is right next to an oxygen, there's not even one carbon in between. It's going to be less shielded, and it's going to have a higher chemical shift. Just know whenever I say something less shielded, sometimes they might call it de-shielded. It's always, whenever I say less shielded, higher chemical shift, it's always in comparison to something else. Alright, let's look at number 5. So this one can be, number 5 and 6 can be a bit harder, and this is when I think it's really good to memorize them. So whenever I have a hydrogen on a double bond, so hydrogen on like an alkene, for example, in this case, it's going to have a higher chemical shift than usual. It's going to have even higher chemical shift than an OH. So hydrogen and double bonds are really, really high. They really have a high chemical shift. So high chemical shift. And take a second and tell me, do you guys think this is shielded or de-shielded? Alright, so whenever I have high chemical shift, I should have de-shielded. Right, so this one, number 6, is a hydrogen on a benzene, or that's what we call aromatic usually. So my hydrogen, it is still on a double bond, but it's on a benzene ring, and that will make it even higher chemical shift than normal, somewhere between 6.5 and 8 ppm. So what does that mean, 6.5 and 8? If you look at the chart that I gave you at the beginning, that's the range. It's somewhere between 6.5 and 8 ppm. That's the range for those hydrogens that are aromatic hydrogens on a benzene ring. That's why this chart is very helpful, because all the examples I gave you are somewhere on this chart. For example, hydrogen on a double bond is right here. That's the range for it. A hydrogen near an electronegative atom is right here. That's a hydrogen that is right next to an oxygen. If you notice, the hydrogen on an oxygen has a really large range. This is a hydrogen on a triple bond. Note that it's an exception. Hydrogen on a triple bond it's not very high chemical shift. It's actually on the lower side of the chemical shift, just somewhere between 2 and 3. So the double bond, hydrogen on a double bond is the highest. It's a lot higher than hydrogen on a triple bond. In this case, I just have a hydrogen on 1 carbon. So there's nothing there. It's very, very, very low frequency. Alright. So the last 2 examples I want to cover are these 2. So when I have a hydrogen on a double bond, but this one it's on a carbonyl, which is just a carbon that is double bond to an oxygen, it's going to be a really high chemical shift. It's somewhere between 9 and 10 ppm. So really high chemical shift. And the last example, which is number 8, whenever I have carboxylic acid, so carbonyl with an OH, it's carbon that's double bond to an oxygen, but they have an OH next to it. So this hydrogen is going to have the highest chemical shift to all of them, because it's right on an oxygen, and that oxygen is on a carbon that's double bonded to an oxygen. So this is a very, very high chemical shift. It's somewhere between 10 to 12 ppm. That's what we have right here. Alright, so if you guys are asking like how would this be helpful, like knowing something that is high chemical shift or low chemical shift, sometimes they can tell you, like they can give you 2 molecules and give you only one NMR for it, and you'll notice that like your peak is somewhere between let's say your peak is right here, somewhere between like 6 and 8, and they give you two molecules, but one of them is a benzene ring, most likely the answer is going to be the benzene ring. Why? Because if you look at the chart, you're going to notice that the benzene ring is somewhere between 6 and 8, right? And they gave you that signal to be somewhere between 6 and 8. So if my signal is somewhere between 6 and 8, most likely it represents an aromatic hydrogen. That's why this chart can be very, very helpful. Alright guys, I will hope to see you tomorrow.